Okay. So, oh, you missed a big long conversation. We'll recap at the end.
Yeah.
Let's look at what's left of the main block. So where did we leave? Did I get to phosphazines? I knew I wanted to. I know we did phosphorus. Oh, no. Yeah, so we did nitrogen. I know we did like, they nitrogen. Before that we did phosphorus. Carbon. Yeah. We did the oxides. All right. So an analog of siloxanes. This is to close out group 15 of phosphazines. These are clusters of phosphorus and nitrogen. Page 468. It's in the world of siloxanes for a while. That's sulfur, silicon and oxygen. And there are analogous phosphazines. Once made an acquaintance with some South African chemists. Like, oh, this is what they were doing, but if you know siloxanes, you automatically know this because they're the same thing. So something like P4 and R6. We've seen this before. Here's a tetrahedron of phosphoruses, and then we're going to bridge nitrogens around it, and bridge at the back also, and at the front. There you go. And all of those nitrogens need to have 3 bonds. So they're all amine nitrogens from this end. And you can make little clusters like this that then will polymerize. And again, it's all in the world of making elastomers, glues and adhesives that stretch. The book has 2 paragraphs. Chains and rings, analogous to siloxanes. The rings are a good place to start the polymerization progress. Doesn't really say much more after that. But you know, you can make sticky glues out of this. Glues that keep their adhesion but still will bend with your material. These are elastomers. All right, that will close out chapter 15. All we looked at in 15 was nitrogen and phosphorus. Let's look at chapter group 16. Group 16. Oh, have I put the chlorines on the wrong thing? Yep, I knew I did. Hold on. That's too many bonds to be around a nitrogen.
Oh, okay.
Nitrogen is not allowed to do that. It doesn't have the availability of hybridizing its electrons into a D. but of course phosphorus can. There you go. You see people muttering, you look at what you've written, you go, oh, of course that's wrong. All right, group 16. Group 15 has a name before we completely put it to bed. In the same way that group 1 was the alkali metals, and group 2 is the alkaline earth metals, and the group 8 is the noble gases, and group 7 are the halogens. Group 15 are the pnictides. I've only ever heard one person use it. Ever. Group 16 go by this name. The H is silent. Do not pronounce the H. The H is as in school. Does not get pronounced. Did anybody pronounce the H in school? School. School. Could start to think. School. Yeah, they are chalcogens. And we have oxygen. Obviously, that's an important atom. Sulfur, selenium, tellurium, and polonium. By the time you get down to polonium, Marie Curie discovered that one, and it or radium killed her. They're radioactive. Selenium has some biological relevance. There is a question about amino acids. How many amino acids are there?
Like 24.
Depends who you ask. Smart Money says there are 20. Well, the textbooks tell you there are 20, but people will tell you there are more than 20 amino acids. Okay. 20, we believe, are coded for in by DNA. And then some of them are essential. 8 of them. Or as many as 10 of them. Or as little as 5 of them are essential, which means that human metabolism doesn't make them. That you have to have them in your diet, otherwise you become deficient and then you die. And 2 of them contain sulfur. Do we know what they are? Cysteine, and then there is a dimer of cysteine called cysteine. Well, there is an amino acid called selenocysteine, in which you take the sulfur out of the cysteine and replace it with the selenium. That is thought to be a post-translational modification. That you build, your DNA builds the cysteine, and then some other metabolism replaces the sulfur for a selenium. But selenium is biologically important. And if you have a deficiency of selenium, I don't really think it matters. Don't really think it's super important. For males of childbearing age, it is. It's important to fertility. Because your swimmers, they have a head and a tail and a little bit that attaches the tail to the head. And if you don't have the right amount of selenium, then the tails don't attach correctly and your swimmers swim around in circles. And because they're men, they won't ever ask to stop and ask for directions. So you're not as fertile as you could possibly be. That's all I've got to say about sliding. I don't know. So oxygen and sulfur it is then. Oxygen, clearly important. Dioxygen is 21% of the atmosphere. And it has bond energy. I should look it up. I started writing. I should look it up. It's fairly strong. I think it's in the high 400s. Hopefully it's in the book. Of course, it's in the book somewhere. Which makes it fairly difficult to split. Come on. I think bond energy has got to be written here somewhere. We'll come back to that. I think it's in the high 400s kilojoules. It's double bond. It's pretty hard to split. But what it does do is it will accept electrons. It's an oxidizer. I mean, that's where part of the name comes from. We don't have to try particularly hard to make metals oxidize. Metals, left-hand side of the periodic table, want to give their electrons away. So metals, as we've come to find out, need to be protected from the environment if you want them to stay around for any course of time. I was looking for a new car at the end of last year, and I almost bought an Alfa Romeo, but I was continuously reminded why we don't buy Alfa Romeos. But you just look back in history. How many of them are still on the road? Well, none of them, because they're all in a pile of dust, rust dust, at the side of the road. For many years, the Ford Taurus was the biggest selling car in North America. You ever see an old Taurus? No. It's like you never see a young pigeon. You never see an old Taurus. Where did they all go? Ford made hundreds of millions of them. And there's none of them left because they just rusted away. If you don't protect your metal to aerial oxidation, that metal just crumbles. Unless you're aluminum. Aluminum's an oddity. The aluminum oxide is actually stronger than the aluminum itself. So, if you look at your pots and pans in the kitchen, if you've got an old cheap aluminum pan and it goes whitish grey, that's just aerial oxidation. That pan is now harder than it was when it was just aluminum. And one of the things we didn't talk about when we were talking about aluminum is aluminum contributes perhaps maybe kind of sort of to Alzheimer's. It's a contributing factor. So if you have only have two pans, if I've got a non-stick pan or an iron pan and an aluminum pan, and I have to make spaghetti and meat sauce, which pan do I use for what? Put the spaghetti in the aluminum pan. when you put tomato sauce in any other pan. Because tomatoes are fruit, and fruits are acidic. And acid will decompose the oxide and dissolve the aluminum into your food, and you don't want aluminum in your food. So this makes that metals exposed to oxygen will aerially oxidize and probably decay. We had the opportunity to talk about this when we did group 1 and group 2 and group 3, but I said I would hold off. The degree of oxidation depends on what your metal is. If we look at group 1 and group 2 are similar, but group 1 shows more of a trend. Let's move down the group. So I've got lithium, sodium, and potassium. At the top of the list, I would need 4 lithiums to react with oxygen to make lithium oxide. This is oxide as the O2 minus. This is something that we all know about. Oxygen is in group 6, now 16. 8 minus 6, well, in fact you go 6 minus 8, gives you 2 minus, which tells me that oxide is a 2 minus. And this is what we base all of general chemistry on, that oxygen is in group 6, has a fixed oxidation state. No, it doesn't. This right here is what we would call our basic oxide. And because it's a metal, you dissolve it in water. The oxides of metals, when you dissolve them in water, make bases. That's your basic oxide. When I let sodium be aerially oxidized by oxygen, I get the sodium oxide. I get Na2O. But it might surprise you that Na2O, sodium oxide, is not sodium's preferred oxide. It actually likes this one. So you're going to get some sodium oxide, Na2O. But this one, Na2O2 minus, is actually the thing that's preferred. General chemistry textbooks ignore this completely, and for good reason. We don't want to confuse the students. We just don't want to tell them too much information at once. Oxides are O2 minus, deal with it. But it's not actually what's going on. What is going on here? What's this thing?
It's O1 minus.
What's this? That's 2 oxygen atoms stuck together with a simple bond. And an oxygen that is bonded twice has no charge. An oxygen that is bonded once has a negative. This is O2, 2 minus. It has a name. What's its name?
Dioxide.
So can we all see what hydrogen peroxide would look like? Hydrogen always makes one bond. Oxygen always makes two bonds. Oxygen always makes two bonds. Hydrogen always makes one bond. Hydrogen peroxide. Hydrogen and sodium are both in the same group, therefore they're interchangeable. Hydrogen can be covalent. Sodium is ionic. Top of the group, you can have a little bit of covalent character. As you move down the group, that covalent character should go away. You should be ionic. You should be metallic. All right. By the time we get to potassium, oh, we didn't balance this. How are we going to balance that?
Put 2 in there.
2 of those. That's it. Potassium, when it interacts with dioxygen, makes KO2. All right, so under our understanding of what's going on from general chemistry, what would be the oxidation state of that potassium? If this is potassium dioxide, and each oxide is an O2 minus, that potassium's going to have a oxidation state of +4, which is ridiculous. Can't have that. So that means that these are not oxides. This is something else. This is the O2 minus ion. Peroxide was O2 2 minus. And this is called superoxide. This is absolutely true in group 1 and 2. As you move down the group, the tendency to make the peroxide and then for it to be superseded by the superoxide increases. I thought I might take a second to talk about singlet oxygen. Or ozone, maybe later. All right, let's move on and look at some sulfurs. All right, so this is true. I said it out loud, I haven't written it down. This is true, group 1 and group 2, where you know what you're getting is ionic, and as you move down the group and you become more metallic, more ionic, you get more of this. The other metals on the periodic table tend to just do the basic oxide stuff. So all metals are going to do this. And then there's a whole bunch of other oxides that are covalent, like carbon dioxide. All of those stuffs, that's covalent. So oxygen gets to be kind of versatile. So metals not in group 1 and group 2. Make the basic oxide, and it makes covalent oxides with non-metals. And it's probably true that if hydrogen is the atom that makes the most number of compounds by combination, oxygen has to come second, because oxygen reacts with a whole bunch of stuff. All right, let's look at sulfur. Sulfur used to be spelled this way. It looks kind of odd to me now because I've adjusted, and it's been 30 years. But more than half of my PhD was on sulfur, and I used to spell it that way. We switched to the F, rightly or wrongly. We switched wrongly. But we've all adjusted. All right, let's look at some allotropes. What's an allotrope?
It comes in different forms. So like carbons come from graphite or diamond or
naturally occurring forms. Allotropes are your naturally occurring forms, and sulfur has a lot of them. Page 482. The big one is S8, but the text gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different variations. And it calls them selected allotropes. That means there's more than 11. And there is a little demarcation in actually the book calls them allotropes and polymorphs. And an allotrope is an individual type of molecule that naturally occurs in the elemental form. And then a polymorph is, how does that pack into a crystal structure? Is it, so we could have, like graphite with hexagonal layers, right? So it would be possible, it would be conceivable for us to go A, B, A, and be hexagonal, or A, B, C, and be cubic. It would still be graphite. It would still only be one allotrope, but it would now have two polymorphs. Same thing, same molecule, but how does it pack? It has at least 11. S8 is the big one. Have you all seen sulfur? Do you know what sulfur looks like? It's a yellow powder. And it does have a bit of a smell to it. That's the trouble with sulfur chemistry. And I know I did a PhD for several years on sulfur. There's lots of chemistry yet to be discovered in sulfur, but people won't do it because it stinks. And not just like, oh, that smells bad. No, it stinks really, really bad, like wretched, bad. Some of the most awful things ever smelled. And they cling, the smells cling to you, and they stay in your nose. And so even like days later, and you've scrubbed yourself and showered multiple times, but you can still smell it. And you're riding the subway and thinking, does everybody else smell dog poop? No? Is it just me? So, this is something we're going to have to learn to draw, and it's not unlike a cyclohexane. It starts like a cyclohexane. It turns into a crown. You have a sulfur at each of those points. It's quite easy to do. That's the big one. But there's S3, S6, S7. We have 3 polymorphs of S8, the alpha, the beta, and the gamma. At one point in time, I knew the difference between the alpha and the beta. I'm not sure I know the difference between the gamma anymore. S10, S12, S18, S20, and S infinity. Let's look what it does in combination with oxygen. Now, things that sulfur does to make itself unpopular. What's this called? A bond from sulfur to sulfur to sulfur to sulfur. What's going on here? When you bond to yourself, we identified what that was called. And the best atom on the periodic table that does that is carbon. Nobody does it nearly as good as carbon. Sulfur catalysts. It bonds to itself. Remember earlier I said that there were 2 amino acids. One is called cysteine, and the other one is a dimer of cysteine called cysteine. Can't stop the sulfurs from touching each other. You've got to keep the sulfurs away from each other, otherwise they stick together. So I've got an organic molecule, I'm not going to talk about it because it's organic, over here, and another one over here. And these are the sulfurs right there. If they come close to each other, they're going to stick. And they make a disulfide bond. A lot of what we wrestle with as chemists is making the molecules do what you want them to do and not what they want to do. And what sulfur wants to do is find the other sulfur in the beaker and stick to it and cluster. And that's typically not what you want. Anybody ever have a perm? Perm? You know, permanent wave? Ever have a perm? Yeah? You got photographic evidence of that?
I don't want to show it.
Was it a loose one? Was it Marsha Clark? Or was it?
They're like little.
You know how that works? Your hair protein has cysteine, which is the amino acid, as a residue in that protein chain. And you loop it up, and then you just acidify and then neutralize. And the proteins relax, and then when you neutralize, the sulfurs stick together, and they now adopt the shape of whatever form you put them in. That's how a perm works. It's living through chemistry. Alrighty, let's look at oxides. The sulfur does a lot of them. We really only deal with a handful of them in general chemistry, but there's a lot more. Okay, page 492. state goes here. Formula. And name. +6. This is sulfite. Oh, you know what? These are the anions. Where are my regular, just oxides? Oh, there isn't a table for just the oxides. All right, so this is as far as we get in general chemistry. We learn sulfate, SO4 2 minus. You have to learn how to write SO4 2 minus. You may even have to draw the Lewis structure. The Lewis structure will eventually reveal to you an oxygen with 2 bonds, an oxygen with 2 bonds. If it has 2 bonds, it doesn't have a charge, and then 2 oxygens with single bonds, therefore 2 negative charges. Hence the SO4, 2 minus, and a sulfur in the middle that has clearly expanded its octet. There's an impossible number of bonds around it. What do you think the geometry on that central sulfur is? All of those, oh, we haven't even mentioned resonance. I'm allowed to do that. So you can't tell which of those oxygens is holding onto a double bond and which of them is holding onto a charge. They are all scrambled over time. So I have 4 equal groups around a central atom, which makes it tetrahedral. And we learn in general chemistry that 8 as a suffix means negatively charged and containing oxygen, and that "ite" means same negative charge, 1 less oxygen. So nitrite contains 1 oxygen less than nitrate, but contains the same negative charge. Sulfate contains the same negative charge, but 1 less oxygen than sulfate. And then we do other things. Sulfur and oxygen are both in the same group. If they're in the same group, then I can change an oxygen out for a sulfur. Okay. And so I get S2O3 2 minus. What's the name of that? This is a solution that you always have on hand in the chemical lab, because it is the antidote to bromine burns. This is thiosulfate. So 8 means negatively charged, contains oxygen. Ite means negatively charged, contains less oxygen than 8. 8 means negatively charged, contains oxygen. Thio means replace and oxygen with the sulfur. The naming system for sulfur compounds is ridiculous. There are competing naming systems at multiple levels for every classification. Thio is interchangeable with something called mercapto. Don't even know. We're not even going to go there. Because mercapto is actually the correct naming system, but thio is better. Thio means sulfur. So look for the oxygen, replace one with the sulfur. Okay, now what we've done, that's central sulfur. Let me look in here, +3. S2, O4, 2 minus. Minuses. So one of those is a double bond and one of them is a single bond. That's dithionite. Dithionite, for those of you that stick in biochemical or bio research, you will end up using dithionite. That's an important agent in a couple of different procedures. I've got a whole page of these, but by the time we get to disulfite, dithionate, and trithionate, I think we're off the script. These top 4 will probably do just okay. Plus, I have to watch the clock. What else have I got? Oh, yeah. Okay, so moving on. Acids we know a little bit about already. We should. Because sulfate is the conjugate base of sulfuric. Acid. And H2SO3 is what? One less oxygen than ick.
Sulfuric.
Us. Eight is to ite what ick is to us. Let me see if we need to talk about the halogens at all. SFN 476. Oh, well, if I want to do tellurium, then yes, I do. Let's look at some halides. S2F2 two bonds. This would be the analog for hydrogen peroxide, where fluorine and hydrogen always make one bond, oxygen and sulfur make two. Always put the lone pairs in for oxygen. One of the things that's going to eventually reveal itself is we're going to talk about some atoms or small molecules as being hard and some as being soft. Sulfur is soft and oxygen is hard. It reveals what the electron cloud is doing. And is that lone pair of electrons really localized, and do I worry about it? All right, we're going to do the F for the CO. Let's do the F. This is in the chemistry textbooks, SF4. This is in the book at the point where we talk about valence shell electron pair repulsion theory. Because if we figure out what's going on that sulfur, there is still a lone pair of electrons on that sulfur. And it occupies this space and distorts this down. And that's why, well, that geometry is bent. This one doesn't get to be tetrahedral or square planar or anything nice. It gets to be kind of an ugly geometry. All right, SF5 actually is going to dimerize to be S2F10. Because in doing so, it gets to be octahedral. SF6 just plain is. All right, if I were to look at the oxidation number for each of these, I could do the same for the sulfurs that I did for the oxygens earlier. This gets to be a +1. This gets to be a +2. This is a +4. Can I keep the fluorides just as F minuses? Fluoride is something that you can probably count on to be a hard F minus true ionic, and therefore you just have to figure out how many negatives do I have, and the oxidation state of my material is the number that counterbalances that. Okay. Sulfur, nitrogen, where are you? sulfur and nitrogen combine together to make these curious little things. You can make S2, N2, and that's explosive. And you can make S4N4, which is less explosive but still unstable. You've got 4 sulfurs here, and then you kind of go around in a ring, and you cross over in the back. You make that kind of thing. But if you polymerize these, make a chain of sulfurs and nitrogens bonded to each other. That polymer is a superconductor. Superconductors have 0 internal resistance to electrical current. And that's something, we see good conductors be metallic, where the metal's close pack, and then the electrons that belong to each of the individual metals are now part of a group, a band. And you can move electrons in that band from one place to another very easily. But even so, there is some resistance, there's some kind of flux involved when you move electrons through a metal. Superconductors don't have an internal magnetic field, which means there is no resistance to electron flow. What happens is, with a superconductor, you usually have to cool these down. When you cool them down, the magnetic field is expressed externally. It's pushed to the outside of the material, not on the inside of the material anymore. And that gives them then the ability to conduct electricity completely on the inside, but it also, because your outside is now a big magnet, it makes them do dumb stuff, like float. You ever see the Japanese trains that float? Japanese have been experimenting with fast trains for like 4 or 5 decades now. And ultimately they're going to make a superconducting train that will go from one place to another super fast. But so if you took a piece of superconducting material at room temperature and you put it on a piece of metal, like on a metal plate, and then you cool it down, when the magnetic field expresses itself externally, it will lift off. It will levitate. Something called the Meissner effect, where you express your magnetic field externally rather than internally, because there's now no resistance. Okay. Sulfur and oxygen. There is actually one useful thing today. Peroxides and superoxides. That's actually useful. Everything else is just a list. Move on. And we will be done. We can do coordination chemistry for the rest of the term. 17. Halogens. All the halogens exist as diatomic homonuclear molecules, covalent bonding. Although, you know, they're all available to do ionic bonding as well. Depends what presents them to themselves. So we know F2 is a covalent molecule. And we know that NaCl is an ionic compound. So we have the ability to do both of those behaviors. What is a little bit unusual are the interhalogens. That these things bond to each other. That should not be too much of a surprise. They're all in the same group. They're all interchangeable. So if I can make F2 and Cl2 and Br2, there should be nothing at all from stopping me from making ClBr or IF. This kind of thing. There should be no reason at all why I cannot make those. They're in the same group. They're supposed to be interchangeable. So take a Cl2 and switch it out with a Br or an F. It's going to work. What is unusual, however, is that you can change the coordination number of the central atom. That's all. And what's not as odd when you look at it, we're going to see XY, XY3, and what will be next on the list? We skipped over XY2. XY5, and then XY7. Why did we skip over XY2 and skip over XY4? Maureen? 1, 2, 3, 4, 5, 6, 7. How many bonds does it make? It makes a bond here with its non-bonding electron. If I force it to make another bond, I have to split its bonding pairs up. Then what's this going to be? XY, XY3, XY5, XY7. These occur because we're splitting up those non-bonding pairs of electrons. Okay. Typically, the atom in the middle is the bigger of the two atoms. And at some point, it's not going to be viable for bromines and iodines to be on the outside of these things. We're looking for big atom in the middle, small atom on the outside. All right, let's look. If I put 3 bonds to this chlorine, it leaves me those 2 lone pairs right there. Go ahead and predict what the shape for BRF4 is going to be. Let's start with that. Make 4 bonds. Oh, I'm sorry. 5. 5. 5. 5. 5. 5. 5. 5. This is 4. We've already established jump in 2s. BRF5. I think that's right. The square pyramid. What's the point group for a square pyramid? IF7. What geometry would IF7 predict? 7 equal repulsive forces around a central atom. Square pyramid. If I rotate it on its vertical axis 90 degrees, I get itself back. So what's its point group?
C4.
And that's on the vertical. deep. Get a pentagonal bipyramid, which is a little bit more difficult to figure out. That's a D5H, because you can do this. Oh, I didn't do the tellurium. Oh, well, never mind. All right, how many groups, how many bonds can fluoride make? It's one of the rules that we write at the beginning of general chemistry when we're learning to write Lewis structures. Hydrogen always makes one bond. Bonds to hydrogen are always terminal. Fluorine always makes one bond. Bonds to fluorine are always terminal. Are bonds to hydrogen always terminal? No, we've already broken that rule. Here we go again. Fluorides can bridge just the way that hydrogens can. If I made titanium F5, titanium F5 will trimerize to Ti3F15. It's titanium. There's titanium. Here's another titanium. Oh, let me see if I can go back from that. Oh, I can do it. Square pyramid, if I draw the pyramid. There you go. Niobium F5 does exactly the same thing, only it does it in a square. And you make each of your metals be octahedral. Okay. Telluriums back. I remember having to learn this. Tellurium does it with bridging iodides. And there's a couple of different polymorphs for this. There's only one in this book, or in this edition of the book. I remember having to learn multiple versions of this. This one's a bit more complicated. I'm going to take telluriums and I'm going to put them in hexagons. Then I'm going to bridge the edges. With iodides. Kind of crazy. Okay, so what we've done the past few lectures is plod across the main group of the periodic table, ignoring the obvious stuff that we already know, pointing out a few oddities, breaking a few rules, and kind of there is some interesting chemistry in the main block. However, all the really good stuff is in the transition block, which we start on Thursday. Completely